Hello everyone. Today we are going to talk about lightweight message authentication codes and authenticated encryption. So let's start with message authentication codes first. Then we will see some examples and some standards in the lightweight standards actually. Then we will move on to authenticated encryption. But let's start with message authentication codes. In short, we call them MACs. So communicating parties share a secret key K, and they can compute an authentication tag T using this K. Actually, this should be capital K. Sorry for that. So idea is as follows. Two parties wants to communicate, but there is no encryption involved in this case. But we just want to be sure that our messages are authenticated. So when I send a message to somebody, they have to be able to check if the message is authentic. So they have to need an algorithm for this. So you might think that maybe we can just simply use hash functions, right? So when I send a message, I also send the hash of it. So when the receiving party takes the hash of the same message, they will obtain the same hash value and they will say that, okay, the message is not modified. No part of the message is modified, deleted, changed, or anything else added. But this idea doesn't work because if an adversary who has ability to modify your message during the communication, they can modify your message. But now, since the message is changed, they can compute the hash of this message again and obtain the new hash and send it together with the message so that the receiving party won't be able to check if the authentication correct or not. So for this reason, we actually needed a secret information between the communicating parties to check the authenticity of the message. So message authentication codes sometimes are seen as like hash functions with a secret key. So idea is as follows. When you send the message, you also send an authentication tag, which is generated from the message authentication code algorithm, which you, as an input, takes the message and the secret key and produces the tag. So sender computes T and sends it with the message. Receiver can verify whether the message has been altered or not by computing the T prime from the message and check if T equals to T prime. Because if somebody changes the message, the T prime would be something else, so they wouldn't match. And if somebody doesn't change the message but changes the tag during the communication, they wouldn't match either, so you would notice that somebody is altering the messages. So this is the main idea. So how can we attack a message authentication code? There are actually two types of attacks. First one is key recovery. Since there is a secret key involved, so one of the attack type would be key recovery. So assume that you are listening to the communication for a long time, so you capture a lot of messages and their tags together. So you have message tag pairs. So assume that you have n many message tag pairs. So from this knowledge, it should be infeasible for an attacker to recover the k-bit secret key K that was used to create the tag. So this is what a key recovery attack is. Your aim is to capture the secret key by looking at the relation between the message and the tag. So if it is a weak message authentication code, then you can capture the secret key from there. But if it is not weak, then it should be hard. So second attack type is MAC forgery. So in this case, the aim is somewhat different. So again, you are given n message tag pairs M1, MT1 to MNTN. So you have n many message tag pairs. So it should be infeasible for an attacker to generate a valid message tag pair M prime T prime, but this time this message is none of the messages that were sent before. So you are forging a new message. Actually, you are sending a new message and forging a tag for it. So you are generating a message authentication code for a message that has not been sent before. So this is why we call it MAC forgery, and you are doing it without knowing the secret key. So this is a different kind of attack, and sometimes it is possible to do it without knowing the key. So if you look at the security, key recovery attack should require 2 to the K operations because this is like the brute force. You can try every possible key and check if when you capture M1 T1, you can check which key produces this T1. So Brute force attack has the time complexity of 2 to the k, where k is the number of bits the secret key k has. Key recovery attack leads to MAC forgery, and this is an obvious relation because if you perform a key recovery attack and capture the key, at this point on, you can generate any tag for any message you want. So key recovery attack leads to MAC forgery, obviously. But for a weak scheme, it may be possible to forge a tag without recovering the key. So you don't have to always capture the key to forge a MAC. Sometimes there are weaknesses in the message authentication codes where you can perform this kind of attack actually. So if the message authentication tag T is of T bits, a successful MAC forgery should require 2 to the T operations. So again, this is the time complexity for the brute force attack. So if you are designing a message authentication code, it should be as secure as 2 to the T operations. If you can break it with less than 2 to the T operations, then we will say that this message authentication code is broken. So it is not secure against forgery. So let's look at some of the examples in the literature. So there's the CBC MAC. So it is cipher block chaining, but this time it is not encryption, a block cipher encryption, but it is actually a message authentication code. And idea is as follows. Remember the CBC from mode of operations for block ciphers. This picture is almost as the same of it, but only difference is that you're not producing any cipher text blocks from here because this is not an encryption. So you again take the first message block, you take the IV, XOR it, and perform an encryption with the secret key, and you're now choosing a block cipher for this operation. So assume that you have chosen AES. So you perform AES encryption, but instead of producing a cipher text block, you take this and XOR with it and so on. You perform these operations until you fit the whole message to this algorithm. And at the end, you perform a final process and produce a tag. So when you're sending the message, you're sending this plain text together with this tag so that anybody who's receiving this message, if they know the secret key, they can perform the same operation and check if the tags match. So motivation is as follows. Last cipher text block is dependent on the previous plain text block in CBC mode. So CBC MAC appears in FIPS 113 with DES being the underlying block cipher. So in a very old standard, this idea was used, but for the encryption, this document suggested using DES because DES was a standard at that time. But today you can use AES or another block cipher or a stream cipher that is secure. So the final process here is necessary to avoid forgery attacks. So this is one way of doing it, but here you are using a block cipher. So this is a message authentication code based on a block cipher. There are some other methods like CMAC and OMAC. This one key MAC is called OMAC, and I think there are a few versions of it. And when you use the version 1, it turns into CMAC or something like that. So I'm not going into much detail, but the picture is like this. So it is like the previous picture, but now you have some tweak here, and actually you're adding some kind of a constant here and produce the output. So again, here you are using a block cipher or a symmetric key encryption algorithm here to perform this operation. Another famous algorithm that is used in the literature is this time HMAC. So instead, the previous two pictures were based on block ciphers. Now we are using a hash function as a message authentication code. So idea is as follows. You have the secret key. You perform a padding to it. So you are actually XORing it with a specific value that's specified in the standards. Now you concatenate it with your message and perform your hash operation. For instance, if you choose SHA-256, you perform SHA-256 on the key concatenated to your message. The output is again concatenated to your key, but this time it is XORed to a different value. You perform a final SHA-256 and obtain the tag. So as you can see, this is two paths of the hash function, but don't think that this operation is takes time twice as long as a single hash, because initially maybe your message is really long. For instance, maybe you are hashing a 1 gigabyte of message, but after the hash function, the output is really short. If you are using SHA-256, now this is just 256-bit value concatenated to your key. So this final hash operation is actually really fast because you are actually hashing one block. But if your message is long, this operation should take longer. So this is used in practice a lot. So probably you heard the name HMAC before. So this is how it works. So in the previous pictures, we use block ciphers. Now in these pictures, we are using hash functions. And you can choose any hash function you want, as long as it is secure, of course.